Good afternoon, everyone. It's Evan Snowman again for Umukhleko, Making a Difference. We're looking at our final example, our final video from the calculus chapter, and today I'm looking at a past exam paper, which I'll look at in full as opposed to cherry-picking questions. The first point I'd like to make is what we see on the picture right now. This is the government's CAPS descriptor of what they expect a student to know for calculus. And for me, you can't play the game if you don't know the rules. So when you are studying, I would very much be guided by the statement and make sure that I know these 9 instructions. Okay? So knowing what a limit is, using a limit to define the derivative of gradient, etc., etc., etc. And make sure that I know these things well. Please recall that for a state paper, knowledge counts for 20%. Routines, so basic questions such as the ones you've seen in textbooks, count 35%. So for me, if you simply study from your textbook and you don't go beyond your textbook, please understand that that means you are capping your mark at potentially 55%. Now, for some people, that is an awesome mark, and they've never had a higher mark than that for mathematics, and that is fine. That's not a problem. If that's your ability, well done. That's awesome. But I do suggest that many of you will want to move your marks into these top 45%. Now, to do so, you need to be able to do what are called either complex routines, complex procedures, or applications. Complex procedures or applications. That makes up 30% of the paper, and only the last 15% is really, really unusual, and that is problem solving. Now, I say that unusual on purpose because for me, that means that actually, if we know our work well enough, if we really know our work well, that means that 85% is actually a possibility. The problem solving, who knows? We don't know quite what they're going to ask. But we do know that actually, if we work only in the textbook, we cap our mark at 55%. We need to be able to know our work so well, know our work, which in this case is these 9 instructions on the left-hand side. If we know our work well, we can aim for marks that go beyond that 55%. Okay, the next thing I want to look at is this table at the bottom, and that is to make sure that we know our chapters, our topics well, and we need to know which chapters are perhaps slightly more important than others. We can maybe target some chapters that are our favorites, and we can maybe, I wouldn't go as far as to say neglect, but we may decide to make less efforts in the chapters that we really, really struggle with. But again, is to make sure that we understand how a paper is set in terms of topics. And you'll notice here that for the topic we are currently doing, calculus, that the differential calculus is worth 35 marks. In other words, out of 120, out of 150 marks, it is worth 20%. Okay, it is worth a full symbol. Okay, so if you don't know your calculus, you are throwing away 10% roughly of your final mark. You are therefore throwing away a full symbol. This one topic can be worth an entire symbol to your final mark. Okay, I've gone and found a past paper. It happens to be the 2018 supplementary paper from the government. Okay, and what we're going to do now is we're going to work through it in full and see how these 35 marks that they refer to here are broken down in the various forms. You'll see that some questions are straightforward, and we'll talk about them, and some questions are less straightforward, and we'll hopefully be able to identify them and work our way through them. So the first thing is we have a question that asks us to work out something by first principles. Now, because it is from first principles, they consider this to be knowledge. Now, I know that many of my students don't like studying things off by heart for mathematics. They will study an entire textbook, 300 pages of biology, 250 pages of geography, but come down to learn 5 examples off by heart for mathematics, not keen on doing so. So please make sure that these marks that are designated as being knowledge marks are marks that you know well. Okay, so 8.1, we know that f prime of x equals the limit as h tends to naught of f of x plus h minus f of x all over h. Again, that statement is on your formula sheet, so you need to know how to use it. But the key thing which I want to go through again is one of the things which we are looking for here is the notation, okay, and then the accuracy of your proof. Okay, so we know that this will be the limit as h tends to naught of 4x plus h squared minus 4x squared all over h equals the limit as h tends to naught of 4x squared plus 8xh plus 4h squared minus the 4x squared that we had from the second term all over h. We know that we want the terms that do not have h's to cancel, and again, in fact, they do. We know we want that so that the terms that are left behind all have h's in them, so we can get a common factor. So we've got h times 8x plus 4h. We want this so that, again, we can get the h's to cancel, so that the problem, which is the h in the denominator, falls away. If it falls away, we no longer have a problem. And so we've got 8x plus 4h. We no longer have a problem. And so as a result, what we're going to get is the h becomes 0. You can put it in if you want to, but what we're going to get is 8x. Now, what I'd really encourage you to do is to forecast the answer again. So we know from this that f prime will equal 8x. And so again, when we get this 8x, we know we have done the correct thing. Okay, the next thing I want to point out to you is that because I knew my work, these 5 marks did not take me 5 or 6 minutes. They only took me 3 or 4 minutes. And so actually I'm gaining some time for later questions, for questions that might be a little bit harder. Okay, 8.2.1. Okay, this notation of d of x, dx, that notation has fallen away. And now they say d by dx instead of saying that notation. So please do not be too surprised by that. Okay, 8.2.1. Okay, d by dx of x squared minus 2x minus 3 all over x plus 1. Again, note the notation. I'm not doing any work yet, so therefore my notation isn't actually changing yet. Okay, I need to deal with this x in the denominator. This x in the denominator is the problem. Okay, the fact that it is a binomial means I can't simply cancel, so that means I will need to deal with it by factorizing the top. The good news is that x plus 1 actually is a factor of the numerator. So we get x plus 1 and x minus 3 over x plus 1. As expected, the x plus 1 will cancel and will go away. Okay, so what I now have is I'm looking for the derivative of x minus 3. And again, notice how the notation changes, how because I'm now taking the derivative, this space here, we no longer have the derivative notations. Okay, in 8.2.2, they're having a bit of fun with us. They're asking us for a second derivative. So we're going to do the derivative once, and then we're going to do the derivative a second time. Okay, and again, if we can do it once, doing it a second time is not a challenge. We just need to have some courage. And we've spoken about this before. To get it into polynomial form, we need to change the surd into a exponent. So we've got root x, but the key is to change this into x to the power of a half. We're now going to track our rules, and it says, therefore, f prime, the first derivative, is going to be a half x to the minus a half. We bring the power to the front, and we drop the power by 1. And if we do it once, we can do it again. Therefore, the second derivative will be bring the half to the front. So we're going to get minus quarter x to the minus 3 over 2. I just want to check if there were any further instructions. No, there were not. There's no instruction to leave this thing in with positive powers. So that is my final answer. There we are. I'm done. Now, all of this would be considered to be knowledge or routine procedures. Okay, both these questions here would be considered to be routines. Okay, and so again, I would be aiming to know my work really well and therefore to be working at roughly or slightly ahead of the idea of a mark a minute. Okay, because we've now dealt with the theory of it here, the first principles and the differentiation by rules, we've done nothing so far with graphing. So again, it does not surprise me that the next question, the very next question, now starts to ask me something to do with a graph. And again, it is not surprising that the matric syllabus involves cubics. Okay, reading through it. The sketch below represents the curve x cubed plus bx squared plus cx plus d, 3 unknowns in this case. That is really quite a interesting example. Already be putting this maybe in the realm of complex procedures because it has 3 unknowns. Okay, the solutions of this thing are x equals naught, f of x equals naught. Sorry, f of x equals naught. The solutions are -2, 1, and 4. Calculate the values of b, c, and d. Now, we've seen similar ones to this before. So yes, it is a slightly more interesting example, but what we need to see here is that the coefficient here is 1, that they've left a equaling 1. We've spoken about this before, that a solution is the same thing as a root, is the same thing as a factor. So we know for 9.1 that normally we would say f of x equals a x minus the first root, x minus the second root, and x minus the third root. But in this case, we know already that the a value is 1. They've told us that over here. And we've actually been told already that the 3 roots are -2, 1, and 4. So what we need to do here is plug those values in and have the courage to see it through. So f of x is going to equal 1 times x plus 2, x minus 1, and x minus 4, which gives me x plus 2 times x squared minus 5x plus 4, which gives me x cubed. Let's check the squares. It's going to be 2x squared minus 5x squared, so minus 3x squared. The x's will be minus 10 and plus 4, so minus 6x, and the constant will be plus 8. So we now know that b equals minus 3, c equals minus 6, and d equals 8. Because again, please do not forget to actually go ahead and answer the question. They asked us for the values of b, c, and d. Having got that, we are now going to move on to 9.2. Again, please remember the importance of the first question in a scaffolded question. Please, if you need to take it a little bit longer, please do so, so to ensure that you have got a solid answer moving forward into the rest of the question. 9.2. Okay, we now know that f of x, as you said, equals x cubed minus 3x squared minus 6x plus 8. We're now asked to find the coordinates of b, the maximum turning point. To find a turning point, we know we take the first derivative and make it equal naught. Again, fairly monotonous by now. Okay. We can divide through by 3 to make my life a little bit easier. Equals x squared here. Okay, minus 2x minus 2. This is not feeling like it's going to be a nice sum because unfortunately this is giving me quite a unpleasant version because we now need to use the formula. Okay, the quadratic formula. I don't have my calculator with me right now, so we're going to work it out quickly by hand. Okay, but I'm going to put this into the formula, into the quadratic formula. So we know that A equals 1, B equals -2, C equals -2, and X equals minus B, so that's +2, plus or minus the square root of B squared, so that's 4, minus 4 times -2, so that's plus 8, all over 2A. So therefore, that is over 2. So we've got X equals 1 plus or minus the square root of 3, okay, which equals 2.72 or negative 0.72. Okay, now the reason I mention that is because I need to think about what it means for B. Now again, one of my turning points is at B, and one of my turning points is over here in line with the second mark I've made here. So the lower value is going to be the one for B, because it is the one that is to the left. That means that this value here is going to be the X value of B. And they've asked me, although they use the word coordinate, they simply ask you for the X coordinate of the turning point, and I've achieved that goal. Okay, so here the last mark was for realizing that the 2.72, while correct, was not the answer they were looking for in this particular question, because they wanted the X value at B. They wanted for us to determine the equation of a tangent to the graph at x equals -1. So in other words, they are looking for, since this is minus 0.72, sorry, let's just get a better way of writing this here quickly. Minus 0.72. Again, here would be -1, for example. So they are talking about this tangent over here. Okay, so some tangent that is going to go through that point there. Let's see if we can get one fairly well. Okay, so they're looking for the equation of that line. Okay, so again, we're talking about a straight line, so y equals mx plus c. We know that a tangent has two things in common with the graph. It has the point of tangency in common with the graph, so that's the first thing, and we know that the gradient of the straight line will equal the gradient of the function at that point. So I need to find f of -1, and f of -1 in this case is going to equal -1 -3 plus 6 plus 8. So that's -4 plus 14, so that equals 10. So we know it goes through -1 and 10. We then need to find the derivative, so we can find m. In this case, we know that the derivative is going to equal 3x squared minus 6x minus 6. And we want the derivative at -1. So that's equal to positive 3, positive 6, minus 6 equals 3. So now we've got everything we want. So we can go sub it in. The y value equals m times the x value plus c. So 13 equals c. And again, if we bought into the fact that this point here had the coordinates of -1 and 10, it should not surprise us then that this y cut of this line is sitting slightly higher than 10. Not massively higher than 10, but slightly higher than 10. And so as a result, we have an answer of the equation for the tangent. But again, please don't forget to answer the question. The equation of this tangent will be, sorry for writing the skew there, y equals 3x is 13. And there's 9.3. Okay, 9.4, sorry. Now they want us to draw a sketch of the graph. But again, watch out. I know that my screen is not the biggest, but watch out because they haven't asked for the first derivative. They've asked us to sketch the graph of the second derivative. Okay, so 9.4, if we follow on from our first derivative, it should follow that our second derivative is going to be 6x minus 6. That's a straightforward linear function. Calculate the x and y intercepts in our sketch. That should not be too difficult. So if here is our set of axes, we know that this thing's got a y cut of minus 6. We know it's got an x cut of 6. Sorry, an x cut of 1. Okay, cool. So we know it's going to cross the y-axis at 0 and minus 6. It's going to cross the x-axis at 1 and 0. And having got our two values, we can simply draw in a graph. Okay, so there is our sketch. And there is f double dash. Okay. Finally, for which values is this thing concave upwards? And again, I would like to remind you that again, the thinking here is what we need to do a little bit of. Once we've done the thinking, the doing is quite easy. And so again, for this final one here, what we're going to realize is that for 9.5, again, I apologize for the layout on this page. I'm trying to put everything onto a single screen. We know that this second derivative, which equals 6x minus 6, for it to be concave upwards, this needs to be greater than 0. Okay, and as a result, we know that the x cut is at 1, and therefore we know that the x value is greater than 1. Okay, the zone we want here is for the second derivative to be positive. It is positive over there, so therefore the x value must be greater than 1. Now, at this stage, we have done 11 marks for the previous question and 17 marks for this question. Okay, we've done 28 marks. Now, I know I'm the one helping you, and I know that I know my work because I'm a teacher. But at this stage, 28 marks could probably have, you could probably reckon on spending 35 minutes on these 28 marks. Okay, together, you and I have only spent about 15 minutes on this time. So we could have worked twice as slowly, taken twice as much time, and been very, very careful with our work to get here. But again, I still suggest that if we know our work well in this chapter, and we know that they're going to ask us these sorts of questions, we can do quite well. The one thing we don't know is what's going to happen with problem solving. Okay? And so this final question here is kind of interesting. It was the last question in the paper. It was actually, if the previous questions were questions 8 and 9, this was question 10. Okay, so again, it looks seductively easy because it is just 2 lines of text. But maybe we need to do some thinking here. We know that this function f of x is minus 3x cubed plus x. We could go and sketch it. It's not a problem to sketch it. We can find its x-intercepts and its y-intercepts quite quickly. Okay. They wanted to have a maximum value of 8/9. Okay. So in other words, they're telling us that this graph right now does not have a maximum value of 8/9. Okay. So if we were to do a quick sketch of it, so yeah, again, I thought us to get that function going. Let's get a quick sketch of it going. Okay, so this is the sketch of f as it stands right now. Okay, we know that the y-intercept will be y equals 0. We know that the x-intercepts can be found by going 0 equals x times minus 3x squared plus 1. So again, no surprises that one of these things is at 0. Okay, and as a result, we've got 3x squared equals 1. And as a result, x squared equals a third, and so x equals plus or minus the square root of a third. So that's quite a fun value. Again, I really don't need to know what those values are. That's the square root of a third and the other square root of a third, the positive square root of a third. Okay, and so we know again, because this is a negative cubic, that the graph will come in from top left come through that x-intercept, turn, go through x equals 0, turn, and cut back through that last x-intercept and exit out to the bottom right, because that is what a negative cubic tends to look like. Okay, so we need to set aside that this graph needs to have a maximum value of 8/9. Now, this Q value simply leads to a up or down shift. So in other words, we are looking for a copy of this graph that might do something along the lines of that, okay, where it has been shifted up. And now wherever this turning point is, it's going to have a y value of 8/9. So in other words, the key question is what are the coordinates of this turning point that I've marked on the original function? So actually, okay, drawing this graph has helped me with my understanding. And because I've worked ahead of the curve in terms of my time, I have some time to spare to look at this. So therefore, to find a turning point, I need a first derivative. I'm going to get minus 9x squared plus 1 equals 0. As a result, I've got 9x squared equals 1, x squared equals 1/9. So x equals plus or minus 1/3. Now, again, if I think about it, because this is the maximum value, and they're talking about the maximum value, okay, because they're talking about the maximum value, I know that therefore the x value for a maximum will be 1/3. So following on my thinking now, I needed to now have a y value of 8/9. So let's actually see what the y value is right now. So the function value, the y value of 1/3 equals minus 3 times 1 over 27 plus 1/3 equals minus 1/9 plus 1/3. Okay, so currently I have an answer of, therefore, this point is at 2/9. So this green point is currently sitting at 1/3 and 2/9, and we want to move it up to a blue position where it now sits at the same x value 1/3 and with a y value of 8/9. Now, having done all that hard work, the final mark actually is really, really straightforward. What then does Q equal? Q would have to equal 6/9 or 2/3. Okay, so again, this was not the easiest question. They did not ask us for a sketch, but drawing a sketch did aid our understanding. Okay, I could have tried to work out and find out if I wanted to what the cube or the square root of 1/3 was on my calculator, and that would have helped. Those are all details that are really useful, but the key factor here was to keep track of our thinking. They were asking us for the coordinates of that turning point and how to shift that turning point up to a new y position. And if we follow the thinking through here, okay, and we use the diagram to aid our thinking, this problem-solving question actually was not totally undoable, although I have to agree that under exam conditions with the clock ticking, I'm not entirely sure how many people would be able to think with this clearer mind as I'm able to do right now, sitting here in a quiet venue. Okay, best of luck to all of you, and I hope to see you in some further videos shortly. All the best.